repeatability and accuracy. So this came up once already in terms of our reflectance-based methodology. There's no clear cause of our outlier. By looking at the repeatability of the results, there's nothing that stands out right now as, oh yes, you had your panel upside down every day. I wish it was just that simple. Oh, we're looking at the silver side. You should have flipped it over and looked at the white side. The white side, that's the spectrum side. The silver side is the metal side. I only heard a few. I'm not sure everybody's getting the joke.
It's black.
It's the end of the day. That's right.
It's black.
It's
now.
black. Ours is silver. It's stainless steel. So it's. Well, that's right. Let's try it. I should have taken the cover off of the ASD. Instruments and personnel of the error sources. The biggest one, though, is correlated errors. All of us just assume independence, and we basically go through the process of just RSS, root sum square. As I mentioned, and we've done this a few times now, my Junge parameter, my aerosol size distribution, is retrieved based on my solar radiometer data, and that solar radiometer data could then create uncertainties in this retrieval of the Junge parameter, which will then affect my aerosol column amount, which then affects my water vapor amount, which then affects my ozone, and then that all goes into the rate of transfer. And it all gets correlated in there as well. The way to handle this is through this Monte Carloing approach, and that's something we can do that's very straightforward. Surface reflectance can be correlated with the atmospheric conditions. Currently, we have no diffuse light correction. The reason, again, was we could not find something that worked reliably. And as I mentioned, as again we start looking for these half% type problems, we may need to have a diffuse light correction. If we change the way we sample, instead of carrying an ASD and walking, if we put the ASD onto a tripod, and you put the tripod, you set it down, you lock it into place, you look at your panel, you make your panel measurements, you shadow the panel, you make your panel measurements, you then move the tripod a little bit, look at the ground, shadow the ground. You do that 15 times on a test site in about a 30-minute time period. Now you have something that's a far better data set that might give us both better repeatability as well as better relative absolute or better absolute uncertainty. Okay. So a lot of this is still, we're talking repeatability at this time, and all of those things in terms of am I wiggling, am I tilting, am I having changes in the diffuse light component, those are all affecting my repeatability. They affect my absolute uncertainty because I may not have put them into my error budget properly at this point. The other thing that helps with repeatability, and this is in general if you're doing any kind of work, laboratory work, field work, watching movies, anything that you want to do well over and over and over again. The better extra information, ancillary, other data that you think is unrelated. It was somebody's birthday yesterday. Well, we'll write that down. Maybe because they all went out and they had a fun time the night before. Maybe they forgot to pack something, and so all they have are black shirts, and that then changed the way the reflectance comes off your shirt. Things that you think that have no impact are just surprising once you start to see the same thing happen over and over because you wrote it down. Pen and paper was always, and I took photos of those people because that's really the important stuff. Now, as the person in charge, I was very lucky because I'm not going to lie. Again. I haven't yet so far. I am horrible at this. So, there's people who are very good coaches, but may not be very good at the sport. And the idea is that if you're not very good at it, you should coach it. And so I'm very good at coaching people to take very good notes. I do not take very good notes at all. So I was very good at finding people who were good at note-taking. And it was a recognition that in order to have a successful field campaign, the people that went on that trip had to cover for my mistakes, had to cover for my lack of ability to do something, or just laziness in some cases. But I brought other things. In other words, I could help solve problems quicker than they could. So you may not be the best note taker, and if that is the case, admit it and find people who are to ensure that you get the notes that you need. And part of the problem was I just would remember things. So somebody would come up and say, we're trying to remember, we got some odd results from January 20th of 2004. I said, yeah, that was the snow day up at Railroad Valley. I think it was pretty cold, so you might want to check to see if the ASD temperature was really not that good. And they would kind of look at you and, okay, and then they would walk away. That works really good as long as you're in your 30s. And then when you become 40, it starts not to work so good. And this paper and pencil or notes or taking things down on an iPad or something, that's really recommended. All of this helps you when you're processing. What's nice is the systems now we're getting is we can process the same day. We can process even out at the test site. Before I left, we got to where we were downloading. I just thought this was incredible. It just shows how things changed over time. We were downloading the imagery as we were driving back from the test site, because we had a wireless connection that was just a Verizon connector through a cell phone. And we would download the Landsat imagery, and we'd have everything processed before we got back to the hotel, an hour and a half away from the test site. I started this business off in 1991, where it took me 6 months to get a 9-track tape from the USGS, the United States, for Landsat, for one scene of one day of one data set for Landsat. And then we'd have to send the tape back because it had byte errors in it, and we had to have it redone. To now, you can have the data right now. It's just incredible. You're so lucky. Yes. Everything's easy for the guy. Say again?
I hear Monty Python sketch.
Is it? Well, it's not an argument.
No,
the parent's dead.
You were lucky. When I was that boy.
That's the. How many people here have to walk to the meeting uphill both ways? In the snow and
Rush.
I'm trying to keep us awake as we go towards the end of
Never had shoes when I was a boy.
The one I like is we would talk about computers, and the big one was, well, you have an 8-bit system. Bits. We didn't even have zeros. And so all of this, this is all humorous to get back to the point of the more information you have, the better you will. And we're still trying to tease out some of the variability that we just do not understand. And some of it is probably because we did not collect enough information. When I go through this in terms of a training class of helping people develop reflectance-based methodology, I still think this is the most important person on every field trip, because which uncertainty is the dominant uncertainty? What dominates our uncertainty budget? Reflectance. Reflectance dominates. So this measurement is the most important measurement, and this person is making sure, because this person, when they're doing the panel, has to make sure they're centered on the panel. They have to make sure they're not twisted. They have to make sure they're not turning. They have to make sure they're not moving. They have to push a button. They have to look at the screen and see that the data set is appropriate, that there's nothing wrong with it. 35, 40 degrees Celsius, you've now walked for 30 minutes, and this weighs 20 kilos. This person is the most important person out there. You're kind of tilting a little bit. Do you know, I'm just going to note this for you, but it's cloudy, so just kind of wait at the panel a little while. Let's see if the cloud's clear. You kind of are now tilting again. How does your spectrum look? You need to optimize the instrument. Because if this gets messed up, it's a wasted trip. Gone. There's nothing you can do. There's no substitute you can make for the reflectance data. And that ancillary information is really important. And it also is just safety. The biggest highlight of my career when I was at the University of Arizona is we did 20 years worth of field campaigns. I never really kept track. It had to be in excess of about 500-600 days at a test site. We never had anybody go to the hospital, ever. And so this person makes sure that does not happen. Because that's the worst thing. Nobody wants to get hurt collecting data for some instrument that's up in space. Data conditioning. So once you have the data, this is all, remember, we're talking about repeatability. So that person with the notes is making sure everything's being done the same way. We do it from trip to trip. We make sure everything's happening the same way. We may have the wrong answer, but we have the consistent wrong answer all the time. That's really what we're trying to make sure of to start with. When you condition your data, basically you allow that to happen as well. You make sure that how the data comes in, what it looks like, the format, how much you backed it up, where you put it, how it's being processed. The notes in terms of how you're processing the data also becomes important. So I showed some of these yesterday where we had the results of the output of the system. It told who processed it, when it was processed, because you might have multiple data. Somebody might process it today, and then someone else may do it a few weeks later because they want to try it with a different set of intercepts for the solar radiometer. Well, unless you have something that shows the differences between those two, because has anybody here ever actually deleted an output file of anything? Yeah, the two computer guys back there. I still have files that I have never even opened that are 25 years old that I'm not even sure I have the software to open them. But I am never going to delete them because I might need them.
Just a quick correction. I've unintentionally deleted things.
Oh, okay.
Never, not intentionally.
So we tend to save things, and because of that, knowing the heritage, and so the computer folks, they call this configuration management. It's just good policy, it's smart. You at least want to keep track. At some point, I'm going to admit I have no idea what that file is anymore because I cannot open it. The name is like Bill.something else, and it makes no sense. I don't even know who Bill is anymore. And there's no note, so I might as well just delete it. But no, it's not taking up any space. So I still have some zip drives if you want one of those.
Do any jazz drives though?
I have a jazz drive too.
Do you really?
I finally found it in a drawer, so I'm going to throw them away in a few months as I start going through them. I just want to double check to see if I can figure out what's on them first. But all of that is, again, it's nice storytelling. Maybe it's jet lag and I'm old and I like telling stories and so forth. But it is trying to keep track of two answers that are going to be slightly different. Knowing why you had two answers for the same problem is really helpful because it helps with your repeatability. You understand where you're getting the differences. Outliers. Yeah.
With the note taking, since it's so important, do you think, well, it is really important, do you think that like people have a systematic list of things to know that would be a lot easier for people to take up a plan, look at the calculation and things like
I know where this is going, I think. There's another personality flaw with the person in front of you is you can send me an email, I will see the email, I will ingest the email, I probably won't respond to the email.
Not a flaw.
No, that's a good idea. Trying to actually come up with a...
Well, because the thing is that for data to be useful and discoverable for someone else, it needs what we call note taking, what I think can translate to metadata. So if we can systematically do it, and people have consistent agreement on what should be noted down, and then we have bits for extra notes.
The CIOS Working Group on Calibration Validation is having a subgroup meeting starting Monday or Tuesday. And one of the topics in there is basically archiving data and accessibility of data to multiple groups, and configuration management type of things. Things that we've always been talking about for the last 20 years, remote sensing and field. The field collections have never really done a very good job of making the data available to a wider group. It's mostly because of the fact that nobody's come up with a standard way to store data, a standard way to collect the data. I would collect data at the University of Arizona for my processing. The French had a different set of data they were collecting. They're both reflectance-based methodologies. So the question becomes, who gets the priority in terms of how they get formed? And usually it was a fourth person, not even a third, it was a fourth person saying, all of you need to put all of your data on the web, and here's what we want you to do. So you have no data, you're not doing anything except telling me that I need to now find 5 people to go through 5 years worth of data, reformat it, and put it in place. So it's something we need to do going forward, definitely. But we have to be recognizing that there's a severe impact to the people who've already collected the
I
data.
think we need the people to do the retrospective stuff, because we have verified this, which we can do it. What we see in the archive, and moving forward, we have
The RADCalNet is going to help that tremendously. And that's one of the other nice things about it is I would rather lead than push. So the idea is that if we can start doing things, people will start to follow, and that we start to develop the data format style, the inputs that are standard inputs. Even though somebody can put all their data there, and then they can say, okay, now if I take those data and reformat it to that input format, and that's what we're doing with RADCalNet, is everybody's collecting differently, but I tell them, in order for me to process your results, I need it to look exactly like this. And surprisingly, they're starting to give us the data that way, because they see the benefit of us processing it for someone else.
So now with this kind of new push, it's not kind of push, for if you publish in an IEEE journal, you can attach data, computer codes, stuff like that. Would you see more people kind of push towards this, actually including, if not the full data set, some data with that to kind of help standardize? Right, so not, within a discipline, you have X and Y, I might collect them entirely different or present them very differently, but if people now start attaching some pieces of that to their papers, is that going to help drive this along as well?
From the vicarious calibration community, not so much.
Okay.
And the difficulty is that even when you start to publish one, it's difficult enough to get a journal publication now with calibration. It's impossible. There's just no easy way to get published now. Because everybody goes, there's nothing new. We're just adding a data point to a sensor. And I agree with that. You should have a methodology change, you should have something that's improved, you should have a large data set, something should be unique. The other difficulty is, the answer is calibration coefficient. And so what you'll typically get as the data would be a top of atmosphere radiance versus the imagery. But what everybody else wants is they want that surface reflectance, they want that Junge parameter, but somebody might not do Junge parameter, they might do an actual size distribution, or they might do a log normal distribution. And then it starts to break down. Oak Ridge National Labs tried to do this in the 1990s as part of the OS, and they started to gather all the field data. And they did a good job. Some of the University of Arizona data ended up there. Nobody ever touched it because nobody could figure out what to do with it. Because we put the raw data out there. And nobody knows what to do with the raw data. Unless you know the panel BRF, but the panel BRF requires you to know what the equation is that converts the data. It was a little unwieldy. Really trying to isolate what the data sets are that people will need in order to make it useful, as opposed to creating more of a problem is the other issue. I know my colleagues in other countries, and I won't list them, but one of them starts with the letter F. They really do not like giving out any data at all, because the assumption is only other people will mess it up. And then they will publish, and then their results will be viewed as not being very good.
also recommend from other communities. So they are building up a global soil database, and with that they depend on people to contribute. So they are setting up a minimum standard set, and people can actually contribute but later to make it useful. And I think for standardization, it will sooner or later come to which database system they're providing. But that they're having the metadata, like SpecQ, which is right now used in Europe, the CSIRO. And for whenever you can put a DOI on it, right now at least in Germany you get a bit of credits for publishing a data set for it.
And just to go back to that, is the DOI concept is, what I said, it's vicarious calibration. For validation activities, so in the land, because again, I know with the working group on calibration validation, we have a calibration subgroup called IVOS, and we have a land product validation subgroup. That group is doing fantastic work with the DOIs, and there the validation community benefits tremendously because what they're doing is they've done a better job of standardizing the types of data. So if you're doing an LAI validation, everybody knows what you need in order to do that validation. Okay? And they make those data available because in order to do a true global validation, you have to have 50 data sets, 50 different test sites. So each group is very important for them to publish for, let's say, 3 or 4 test sites. And they use the DOI approach to make those data available readily, and they maintain it on websites and so forth. So I think if those people keep pulling in that direction, then vicarious calibration will end up there as well, beginning first with like Libyan desert data sets, which are the intercomparisons with the pseudo-invariant sites. Those are very similar to what you would have with LAI. Something like reflectance-based calibration, the RadCalNet I think is going to have the best effort in terms of standardizing an input format. And then people will, if they want to, they'll make the data similar to that. Educating new scientists and younger scientists is the best way to pull the old guard like me along. It's a completely different way of thinking now. And I'm still half in the, my computer's black. I have no idea what kind it is. It's just something USB, gosh, USB drives. Really? I have a CD-ROM. Can anybody read that for me? So there's a recognition that there's different generations, and again, like I realize I'm not a very good note taker. I'm not up on technology, so I'm trying to make sure I'm not an impediment to changes. It's just whether I can help lead that, that's another question.
Just a short comment, actually. There's this new data journal, where you can actually publish data with this style function. But what they say is that the length of the paper is better, and as long as possible, or that's needed, but everyone should be able to introduce data the same way, in case they are listeners. And the most important part of that journal papers are supposed to be the validation. So that's what they actually write in the instructions, author instructions.
And the struggle we have is the validation community does not consider calibration to be part of their community. The metrology community, you can go there and we're accepted, but then the results are buried and nobody ever sees them ever again. And so there has to be a recognition someplace that data sets for calibration. And again, so my colleague Eric Vermote, who's doing a lot of the calibration for MODIS and VIIRS and ADHRR using the Libyan desert, he is very well tied into the land validation community. So I think that if you begin that process of going into something like a data journal, that might then allow the truer kind of absolute calibration techniques and the metrology concepts to work their way back into the literature. If you go back to the 1980s, almost every paper in remote sensing and environment, the old original classic one, the great one, there was large chunks of every paper was calibration related. A lot of the papers were calibration. It's very difficult, unless it's a special issue, to get a calibration paper into any of the journals. Even, so I will point out that there is a journal as part of one of the societies, not IEEE, that when Terra had its 15th anniversary, we tried to do a special issue on the calibration of each of the 5 sensors on Terra. And the argument was, nobody will ever read it, nobody cares, and it won't help my impact factor. So thank you, but no thanks. Terra, the flagship mission of Earth remote sensing from 1999, is not worthy enough of a special issue in 2015 on calibration. And even then, they still, what they wanted, the person said, well, is if you can bring beers into it, I might consider it. Well, beers, that's MODIS. I don't want to do a MODIS paper. I don't want to do a MODIS issue. I want to do a, so it is, apologies, I tend to get upset and be bothered. I have a lot of pride in some things, so. That one, I think somehow I miscopied some things here. There we go, that's. So this one you've seen a few times. This is that Monte Carlo approach. If we're going to look at repeatability, how do we get at the knowledge of what are our largest uncertainties? How do we get the correlated uncertainties in there? And the Monte Carlo, then what you have as your biggest problem is, are you putting the probability distribution functions for your inputs in there properly? And it becomes, so now you start thinking about, not only do I have to know, and this is why I like reflected space method, not only do I have to know how to do measurements of the ground, not only do I have to know how to carry an ASD without falling over, I have to know radiative transfer, I have to know atmospheric measurements and atmospheric characterization. Now I have to learn about metrology and the dome, and guidance for uncertainties and measurements. And now you're telling me I have to learn all about statistics and probability distribution functions and modeling of that so I can do a Monte Carlo, so I can get my uncertainties so that somebody can tell me that it's just the atmosphere. But it's, for me, it's what I like. Is I enjoy this ability now to start looking at plots like this, and you don't have to go on a field trip. As long as you have a computer that you can run the model on, you can start understanding things, and then you can do a field trip and see if it works out and matches. So all of this is really nice in terms of trying to come up with different ways to understand the repeatability of your system and trying to pick out, well, is it my measurement of water vapor or angstrom or reflectance that's most important? Out of the shortwave infrared, it's all because of reflectance. So there, if you remember those curves I was showing about the ASD, it's, did I warm it up properly? And is the swirl bands all going bad because there's a thermal problem in those in-gas detectors? And how do I get rid of that? Well, then we go back to the comment of, I probably need to take a panel measurement every time I take a data point. And that gets rid of it right there. I need to optimize every time. So that means instead of having 5,000 data points, maybe I only get 15. But my spatial assessment using imagery tells me that that's still a factor of 3 more than I need to statistically sample the test set. It all starts to fold together. It starts to tell one single big story if you let it do that for you. So other things, titles, I apologize, something happens to the fonts here. But this is again looking now at repeatability. What's in here, this is Railroad Valley Playa, this is Ivanpah Playa. It's looking as a function of aerosol optical thickness, and it's the retrieve coefficient, the counts per unit radiance, and these are for Landsat data. And basically the idea is that looking at the different sites and looking at how things vary as a function of aerosol optical depth. Most of us would say that we would expect to have largest errors when we have large optical depths. So you would expect to see all these big outliers out here, and you would expect to see this growth like this. And there isn't any growth. And in fact, one of the biggest outliers we have is at one of the lowest optical thicknesses. And this was one of the snow days, not the snow day that was really good, but it was one of the snow days at Railroad Valley. Again, shows you I don't even need notes. Where it was just really, really brutally cold. The optical thickness, the visibility was a couple hundred kilometers. It was incredibly clear. It was a beautiful day. And it's one of the worst data sets we've ever had in terms of comparison. No idea. The same thing over here at this, Railroad, that one was at Ivanpah Playa. It was again the same thing. It was a very cold day in January. This was another one where you have a fairly low optical thickness, but a large uncertainty. a large difference in core repeatability. And if it doesn't, if anything, it goes like this. So is that because when we have low optical thickness, we're still making a big mistake on the reflectance? It's the same mistake on reflectance, but when we have a larger optical thickness, we actually mitigate the error because of the surface reflectance. So now, here's a sensitivity analysis I can start to do and start to see if maybe there's subtle differences in reflectance that actually improve my uncertainty and repeatability. So all I have to do is just make sure I'm measuring the surface on days that the reflectance has a certain value. That's not easy to do, by the way. That you're sitting in your office and you go, I'm only going to go to the site where I know the reflectance is 0.28. It doesn't work that way, unfortunately. Size distribution. So again, Yoga parameter, we've talked about this. One, it tells us that a lot of the values cluster, and that's self-selection. We're picking days that are clear, we're picking days that are nice, we're picking days that it feels good to be out there, and everybody's enjoying life, and so everything tends to work that way. There's our one weird outlier data set again. That was the low optical thickness. It also happened to be a long Yoga parameter. So maybe it was wind blowing dust, there just wasn't very much of it. So maybe it was because it's a slightly different type of aerosol than we normally have. We did not have Snell data, so we can figure out if that's true or not. This is one that at least makes us feel a little better. It's a large outlier, and it's at a large unit parameter. And so this one is smoke. And this was one of those where we saw this one, we went, okay, now we know when we start to see smoke on either the Snell data for Railroad Valley or Ivy Bar, we know there's pollutants. Just don't even go. It's not even, go back to the hotel and go watch cartoons or whatever is interesting on the television. I was going to say Teletubbies, but I'm sure nobody knows what that is anymore. There's a few. That was the only, when we got back from Railroad Valley, Teletubbies was at, it's the four, I just know Lala's the only one I remember now, and Poe and Roe, and it was the only show that was on when we got back to the hotel. Because Ely did not have cable, and so it was brutal. But again, it's one of those where they're scattered, there's not great repeatability, but there's no clear effect that we can point to and say, here is the cause of our problem. Reflectance. So what this basically says is wet or dry. Most of the cases, you know, everything kind of clusters at a given set of reflectances here. And in this case, there's multiple bands that we're showing, and I can tell because the calibration coefficients get a little different. So left is Railroad Valley, right is Ivanpah. I think the top is band 3 of Landsat, the bottom is band 5. Band 5 of Landsat. The reflectance, that's the nice thing about these test sites, is if it's dry, they basically pretty much always have the same reflectance, and everything clusters. Does that mean that this outlier here is because of an atmospheric effect? Or is it just because of the reflectance wasn't measured properly on that date? It's frustrating. You look at this and there's just, again, no easy answer. We've even had wet days where we got good results, which again, the reflectance-based method should not matter if we're measuring the site if it's wet or dry, but it would matter because you get spatial heterogeneity that's different, so your sampling might not be good in that regard. Other atmospheric effects, the ozone correlated, low ozone amounts give overestimates, predicted gradients. That's band 2, so that kind of plays into a role. Column water vapor did not show any type of correlation with the calibration coefficient. Aerosol absorption, we haven't really looked at that. But that sort of comes into the user parameter case. Resampling. Still trying to figure out why this font comes up this way. But again, basically showing the average of, if you go, and this goes back to is how many data points. We know we have a repeatability issue. And the question is how many data points do I really need in order to prove that the calibration coefficient I derive matches the actual calibration coefficient to a level of confidence that is close to my absolute uncertainty. It's a roundabout way of saying that because I have this large scatter, and I'm only going to make a few measurements, I want to make sure that the answer I give to somebody for absolute calibration is within 2.5% 1 sigma. But when you have a 2.5% variability because of relative uncertainty, you can get something that's 6 or 7% off of the right answer, and that still matches all of your statistics. If you get 5 data points, now you have a result that you have great confidence at the 95% level that the answer is going to be within your confidence interval of 2.5%. And we basically tried, so we started with 2, we started with 3, 4, 5, 6, 7, 8. But at 5, basically you end up with a case where all of the statistics worked out. When we, again, looked at the results, we had 56 data points, subsampled to 5, did this 10 times. And again, that was what I needed for statistical significance with the test I was doing, and found that it agreed to within my confidence interval with the right answer. And the right answer in that case was the average of all the 56. So it becomes how many data sets do you need to pull out of a group of 56 that you are representing the population. And again, I could have just gone to statistics and gotten this answer without having to do it with a spreadsheet and a Monte Carlo simulation, but I did it because I know how to do brute force more than I know how to read a book. That was sort of a joke. I know how to read a book, I just know how to do statistics. I know how to do Monte Carlo better than reading, I guess. Same thing, and I showed this the other day, yesterday, where if we got rid of all of the bad aerosol, and bad ozone, and bad Juncker parameter cases, what kind of average do we have? And this just shows that the repeatability is there regardless of the atmospheric conditions. So we ended up with 12 data sets, and the results still agreed to within the statistical significance of everything involved. So that's, again, what's nice is this is 12 data points versus 59. I can subset and get the right answer. And if I subset based on physics, I'm only going to use really good atmospheric days. I don't change my answer. And that one says that there really aren't that many bad atmospheric days. But 2 is that the atmosphere is not playing that big of a role. Season, so day of year. This is basically a sun angle effect. So as the sun angle changes, do I see things? But it can also be winter tends to be wetter, winter tends to have more clouds. Summer, it tends to be harder to operate the instruments. We tend to collect more data sets around clusters of time. But you see, we're pretty spread out in terms of time of year. With day 150 to day 200, that basically shows that when we go up to a railroad valley, I think this one, yeah, that it's just easier to go in the summer when there's more students available. So that's why you tend to see some of the clusters there. But there's no, again, obvious thing. Here you have a winter case that's an outlier. Here you have a spring case that's an outlier. So there's nothing, again, that says, here is the answer. What I keep telling people is, before I moved and got distracted by other things, what I wanted to do is take all of the inputs and all of the results and basically do a principal components analysis and see if I could find all the kind of the cross correlations between them. I just want to say the eigenvalue of the eigenvector for the reflectance-based calibration shows that the test site surface heterogeneity, the different sizes, we've talked about this already, but we can look at it from now a repeatability standpoint as well as we can from just whether it's a adjacency effect issue. Again, no clear cause. Bad news, there's no easy fix. The instruments personnel, both of the problems. We basically can start looking at the correlated errors. I've mentioned this multiple times. And this is going to be for the next kind of generation of people doing this type of work, both in the product validation and in the instrument calibration work. And this will be especially important when you start trying to do comparisons between hundreds of systems doing the same kind of measurement approaches.